So this is Brian and Keith doing our presentation for the winner-takes-all and vector matrix multiplication circuits. So the winner-takes-all circuit is probably easiest to think about when you compare two. Start by comparing two nodes. So there's a few different components to it. Most importantly, it has a series of input currents and then gives off output voltages. So here we have our input current coming in to transistor here. This kind of rectangular structure is a current conveyor. Down at the bottom we have a kind of current source with a fixed bias voltage pulling through a reference current which comes through all of these kind of terminals here. So these come all the way from a PFET which is connected to VDD and then connected to your Vout as well. So the best way to think about this is if you have two input currents which are the same, so I1 and I2, if that's the case, then the gate voltages of each of these lower transistors must be the same, as IN1 has to flow all the way through this transistor to get to ground. So yeah, because the gates are connected here, actually they always have to have a common voltage. So if the first input current were to increase slightly above the value of the second input current, well, first of all, this would cause a rise in the common voltage here. So if the gate voltage of this transistor were to increase without the input current here increasing, then the source voltage here of this transistor would have to decrease by a lot more to compensate for that. So this is obviously the gate voltage of this middle transistor here. So that gate voltage has decreased by a large amount. So that means I2 has effectively dropped to 0. So if there's no current coming through this upper PFET, then Vout2 must rise up towards VDD. And conversely, because we have a fixed current coming through here, I1 must have increased, so Vout1 must have decreased below the previous value to increase the current which is coming through that terminal. And then you can just extend this concept to have kind of n different input currents and output voltages.
So looking at our winner-take-all circuit here, our focus will be on the blue and the teal lines because those are the input to this T-gate, and the purple line is the measured voltage. So when the teal line is high, we will actually be looking at the output of this winner-take-all circuit. So initially blue, the input of this WTIA is higher than the other input, so purple will be low because this WTA will have 1. And when we come back to the other time teal is high, blue is low and green is high, where blue is the input to this WTA. So because it's low, it will have lost and the purple will be high.
So the main focus of this assignment was to facilitate the vector matrix multiplication. So we had our weighting matrix, our input vectors and our output vectors. So our input vector was a matrix of 4 different voltage vectors which was multiplied by our weighting matrix to give our output current matrix. So the way in which we were able to, the way in which the weighting matrix works is that each voltage component of the vector is fed into a matrix of floating gate capacitor transistors, and in order to control the weighting, the charge on the floating gate capacitor is controlled. So this sets the gate voltage of each individual transistor, and hence comparing two transistors which have the same source voltage, the one with the higher gate voltage will see a higher output current. So here we have these transistors in the same row here correspond to the elements in the same row of the weighting matrix, and hence the currents which come out of those are summed to give your total output current in your output vector. So for our input voltage vectors, we had the 4 different 2-bit vectors with a 1 adjoined to the end of them, and then the task was to find the right weighting values such that we obtained this output matrix here. So the key things about the output matrix are that each different row gives a different logic gate output, so the exclusive OR, the AND, and then the NOR gate outputs with respect to these input vectors which we gave. So when we multiply W and X together, this is what Y looks like in terms of the components of W, which is a bit of a mess. But the important thing after this step is that we use the winner takes all circuit to select only whichever of these output voltages is highest. So we're looking to get this form of output. So for example, we need W33 to be greater than W23 and W13, and effectively we get 4 different constraints on our different element values for the weighting matrix. So taking all these different rules into account, we ended up getting or obtaining these values for the weight matrix, which results in these output values.